This video is designed as an overview of sections 8.9 through 8.13 in the textbook. We're going to look at adding categorical variables to multiple linear regression models. Throughout this video, we will learn what an indicator variable is, perform multiple linear regression with additive models and interaction models. We'll also assess additive and interaction models using an F-test and use AICs for model selection. In some situations, it may be interesting to look at the impact of different subpopulations on a linear model. Perhaps we want to see if there's a difference between two groups. Adding a categorical variable to a multiple linear regression model will result in an indicator variable. The indicator variable is made up of zeros and ones, with the 0 representing one category and 1 representing the other. The true linear model includes the y-intercept coefficient, beta naught, the slope coefficient beta 1 times the quantitative predictor variable, the coefficient beta 2 for the indicator variable representing the indicator variable for the group 2, and epsilon I. Remember, these epsilons should be normally distributed with mean 0 and variance sigma squared. For any observation I in the baseline category, the indicator variable equals 0 and the model is yi equals the intercept plus beta 1 times the predictor variable plus epsilon I. For any observation I in the non-baseline, the deviation category, the indicator variable equals 1, and this model has a y-intercept of beta 0 plus beta 2. We can test that there is no difference in the y-intercepts when the categorical variable has two levels. This tests that the slope coefficient for the indicator variable is equal to 0. We will look at the t statistic or create a confidence interval for the coefficient. Let's work through an example of SAT math scores as a predictor of first-year GPA comparing male and female students. Looking at the scatter plot, we can see that there may be some differences in the relationship between the SAT math scores and the first-year GPA based on gender. We can fit the additive linear model with the quantitative predictor of SAT math score and gender as an indicator variable used to predict the first-year GPA. Males is the baseline category for the indicator variable. Here are the estimates for this model. This shows that the female model has a higher y-intercept than the male model. For this study, we can test the null hypothesis that there is no difference in true y-intercept between males and females in the SAT math model, which would be looking at the coefficient subscript 2 is equal to 0, or the alternative, there is a difference in the true y-intercept between males and females in an SAT math model where beta 2 is not equal to 0. Based on this t statistic and p-value, there is very strong evidence against the null hypothesis that there is no difference in the true y-intercept in an SAT math model for first-year college GPA between males and females. This is based on a t statistic of 7.184, where the t distribution under the null has 997 degrees of freedom and a p-value of less than 0.0001. So we can conclude that there is a difference in their true mean GPA levels controlled for SAT math. The confidence intervals are given here. If we interpret the slope coefficient for the indicator variable, we are 95% confident that the true mean GPA for females is between 0.228 and 0.399 points higher than for males after adjusting for the SAT math score in the population of students. This example only showed if we had a categorical variable with two levels, but we may have categorical variables with more than two levels. It is important to always define the indicator variables in our additive model. The description of the headache example is on page 349 in the textbook. Essentially what they were looking at is that subjects were initially exposed to a tone, stopping when the tone became definitely intolerable. This was measured as DU, and the decibel level was recorded, the variable called DU1. The subjects were randomly assigned one of 4 treatments, and then they measured that same variable again, the point at which it became definitely intolerable. Here we can see a scatter plot showing the relationship between DU1 and DUI, separated out by our 4 different treatments: control, treatment 1, treatment 2, and treatment 3. The linear model for this additive model is given here with our corresponding estimates. B0, which would be the y-intercept, B1, which is the slope coefficient for the predictor variable DUI, B2, which would be the coefficient for the indicator variable for treatment 1, B3, which would be the slope coefficient for treatment 2, and B4, which would be the slope coefficient for treatment 3. Notice that the baseline here is the control. These estimates are used to write out our model. When we find the model for control, our baseline model, we're substituting 0 in for the indicator variables for all of the other treatments. So the simplified model becomes du2 sub I, that expected value, is equal to 0.252, the y-intercept, plus 0.837, the slope coefficient, times the variable du1. For treatment 1, we put in the value of 1 for the indicator variable for treatment 1 and 0 for the other 2. So here we can see that our y-intercept has increased to 0.81. For a 1 decibel increase in DU1 for treatment 1, the expected average definitely tolerable tone, DU2, increases by 0.837 decibels. This would be the interpretation of the slope coefficient for DU1. Let's look at these assumptions for this model. Here we can see some effect plots for DU1 versus DU2 and our different treatments. It doesn't look like there is much variability within these. If we look at the residual versus fitted plots, we can see that there's some evidence against normality, as there is some heavy tails in the QQ plot. There's also some evidence against constant variance, as there's some increase in variance as the fitted values increase in both the RF and the scale location plot. Not seeing any issues really with linearity, multicollinearity, which we can look at the GVIF, and we can see that all those values are less than 5. We're also not seeing any issues with no influential points, as there are no values with Cook's distance greater than 0.5. If we compare the adjusted R-squared value for the model with treatment and DU1 to the simple linear regression model given here, we can see that the adjusted R-squared is larger for the model with treatment than for the simple linear regression model. It appears that treatment is a useful variable in this model. Next, we'll look at the interaction model. We're looking at different slopes and intercepts for our models. It is not reasonable to assume that the slopes will always be the same for all groups. When we look at an interaction, we will look to see if there's an interaction between the quantitative and categorical variables. In the population model, we have an additional coefficient for each interaction between the indicator variable and the X variable. The F-test for the interaction model will test if the slope is the same for all groups in the population. To test which is the best model, we can use this flowchart. If the test for interaction shows that the interaction is significant, then the interaction model is the final model. If the interaction is not significant, then we will fit the additive model. If both the categorical and the quantitative variable are significant, then the additive model would be our final model. If only the quantitative variable is significant, then we should fit the simple linear regression model. If the quantitative variable is not significant, but we see significance with the categorical variable, we can fit an ANOVA model. We can then check these last models for significance to decide what works best for the final model. The F-test is used to test for both the interaction term in the interaction model and the categorical predictor in the additive model. It follows an F distribution under the null hypothesis of j minus 1 numerator degrees of freedom and n minus 2j denominator degrees of freedom. If the categorical predictor only has 2 levels, then we can use the t-test to test the additive model. We can also use the AIC to choose the best model. This gives an estimate of the distance between a candidate model and the true model on a log scale. The smaller the AIC, the better the model. There's a few recommendations when using AIC. Consider a suite of models and find models with the smallest AIC results. The suite of candidate models need to contain at least some good models. Selecting the best of a set of bad models does not make the model good. You should report a table with the models sorted from smallest to largest AICs. Always include the mean-only model. This allows you to compare the top model to one that does not contain any predictors. Interpret the top model or models if a few are close on the AIC scale to the top model. Do not report p-values or call terms significant when models are selected using AICs. Hypothesis testing and AIC model selection are not compatible philosophies, and testing a model selected by AICs invalidates the tests as they have inflated type 1 error rates. You can describe variables as important or useful and report confidence intervals to aid in the interpretation of the effects in the selected model or models, but need to avoid performing hypothesis tests. Remember that the selected model is not the true model, it is only the best model according to AIC among the set of models you provided. Model assumptions need to be met to use AIC. Looking at the dyslexia example that is given in the textbook on page 356, talks about the relationship between nonverbal IQs and reading accuracy, and they want to see if this differs between dyslexic and non-dyslexic students. 2 groups of students were identified, one as dyslexic, and then a group of gender and age similar student matches were identified for a total sample size of 24. We'll start with an interaction model for this study. The estimated regression model shows the predicted reading accuracy score is equal to the y-intercept from this model, looking at our estimates, of 0.8759 plus the slope coefficient of 0.0583 times the variable zig, which is the nonverbal IQs, minus the slope coefficient 0.2795 times the indicator variable for yes, those that do have dyslexia, minus 0.0729 times the indicator variable times the zig variable. If we test the slope for zig is the same for those with and without dyslexia in the population against the alternative that the slope coefficient for zig is not the same for those with and without dyslexia in the population, we can use our ANOVA F-test to give us a F statistic of 3.6357. This is from an F distribution with 1 and 40 degrees of freedom and a p-value of 0.06375. Based on this p-value, we have some evidence against the null hypothesis that there's no difference in slopes between those with and without dyslexia in the population. So perhaps we're not really seeing that there's any evidence of a difference between those that have dyslexia and those that do not. If we look at our diagnostic plots, we can see that there is definitely some issues with constant variance, as we have a cluster of scores down here and some scores that are much more varied for the larger fitted values. The text gives us some reasons for why we might be seeing these differences. Next, we're going to fit the additive model. So we're removing the interaction, because we only saw some evidence against the interaction term. Here are the estimates for our regression model, giving us a predicted score equal to the y-intercept of 0.8918 plus the slope coefficient of 0.0262 times ZIQ, which is looking at the nonverbal IQs, minus the coefficient times the indicator variable for yes, has dyslexia. For this, we'll test that the y-intercept for the model with ZIQ is the same for those with and without dyslexia in the population versus the alternative, that the y-intercept for the model is not the same for those with and without dyslexia in the population. Looking at the ANOVA for this test, we can see an F value of 47.371 for the variable dyslexia, whether or not they have dyslexia, and a p-value less than 0.0001. Notice that this p-value is the same as we see for the t-test. Remember that the t-test will give an accurate p-value for the test of the indicator variable if there are only 2 levels of our categorical variable. Based on this p-value, there is very strong evidence against the null hypothesis that there is no difference in y-intercepts for the model with ZIQ between those with and without dyslexia in the population. This is based on the F statistic of 47.371, an F distribution under the null with 1 in 41 degrees of freedom, and a p-value of less than 0.0001. We can conclude that there is a difference in y-intercepts for the model with ZIQ between those with and without dyslexia in the population. Do have the output here for the AIC, and this AIC, the smallest AIC, is for the model that is including the interaction term. We only saw some evidence that the slopes differ, and that these other 2 models here, this is the model with only the categorical variable, and then the model with the categorical variable dyslexia and the IQ, are all within the bounds of 2 for the change of AIC. So all these models might be useful in explaining the relationship between IQ and the reading accuracy. Based on our analysis, it appears that the additive model does show some evidence of an association.